Chromatic Elemental Imaging, or CEI, is a high-resolution imaging technique used to identify Foulant in vivid color. To illustrate this technology, we will review a case study where CEI was crucial in fully understanding and troubleshooting a complex situation at a beverage facility in system failure. The facility was experiencing issues with the last stage of their reverse osmosis system. Prior to sending the element to Avista Technologies for autopsy, they performed a clean. However, the clean was unsuccessful and did not restore permeate flow to their system. When they removed the element from the system, the weight was recorded as 57 pounds, which is at least 22 pounds of Foulant material trapped within the element. The membrane was dissected, and chromatic elemental imaging was performed on the sample harvested from the full element. Before us, we see the peaks and valleys of the Foulant deposited on the membrane surface as we would during scanning electron microscope or SEM imaging. SEM allows us to see the morphology or shape of the Foulant material. However, SEM does not tell us the composition of the material. We pair this technique with energy dispersive spectroscopy, or EDS. EDS tells us the relative concentrations of the different elements throughout the Foulant. Although we now know what elements are present, we cannot see how these elements interact to form compounds or how they are layered in the Foulant. But what if we could see where the carbon is present, where the calcium is located, where the fluorine resides, and finally, the distribution of the silica in the Foulant? Welcome to the wonderful world of chromatic elemental imaging, or CEI. Through this technique, we can visualize the composition of the Foulant to understand it better than we've ever been able to before, and to tell the full story of the life of this membrane. We see the large crystalline structures are calcium carbonate in purple, a mixture of dark blue carbon and red calcium. The granular material is calcium fluoride in orange, a combination of calcium in red and fluorine in yellow, which is deposited around the calcium carbonate crystals, indicating the calcium fluoride deposited after the calcium carbonate. Finally, when we look at our most underlying layer, we can see that it's composed of silica. If we relied on EDS alone, we may have discounted silica, as it was present in much lower relative concentrations when compared to both calcium and fluorine. Additionally, colloidal silica has a granular texture, which may have led us to believe that it was part of the granular Foulant layer. With CEI, we can positively identify the underlying layer of botryoidal material as silica. By understanding the layering of our three distinct Foulants, we're ready to tell the full story of this membrane. This is a new membrane. As pure water is being removed from the feed stream, sparingly soluble salts become more and more concentrated. If the salts reach a point of supersaturation and overcome the additional protection of any online antiscalants, they may precipitate onto the membrane surface in what we call scale, blocking permeate flow. Silica deposits in a very thin layer on the membrane. The site already knew that they had the potential for silica scale, and they were dosing an antiscalant that targeted silica. However, the dose was based on an old analysis, and the silica levels in the water had since increased. After the formation of silica, due to the changes in element hydraulics and the creation of nucleation sites, calcium carbonate precipitated. As the site noted a loss in flow in their last stage, a clean was triggered. Since they only suspected silica, they cleaned with ammonium bifluoride, a dangerous chemical which must be handled with extreme caution. The site did not monitor the pH of their clean, not knowing that calcium carbonate was present. As calcium carbonate dissolves, it raises the pH of the cleaning solution, and if the pH is allowed to exceed a certain level, calcium fluoride can then precipitate, as we see here. Knowing this information, we were able to make recommendations to clean and prevent the Foulant. RoClean L403, a buffered low pH cleaner, was chosen to remove both the calcium fluoride and calcium carbonate layers. RoClean P112, a high pH targeted silica cleaner, which does not carry the hazards associated with ammonium bifluoride, was used to remove the silica layer. The site cleaned on-site and replaced elements weighing more than 50 pounds, which are often considered irrecoverable. During this time, an updated water analysis was performed, and Avista Advisor CI was used to predict what scales would form and what antiscalant was needed to prevent them. Vitek 4000 was chosen to inhibit both silica and calcium carbonate. After Vitek 4000 was put online, the site achieved stable system performance. Scaling was no longer observed in the last stage of the system. As a result, the site was able to reduce their cleaning frequency to biannually for front-end organic fouling. This is just one example of how CEI has taken foulant identification from black and white to color.